this video, we're going to have a look at prime factorization and its applications. Any whole number can be broken down into a product of prime numbers that is unique to that number. It's like a fingerprint or the building blocks of that number. For example, 20 can be written as 4 times 5. 5 is a prime number, but 4 is not. So we'll break 4 down into 2 times 2 times 5. Now they're all prime numbers. Normally, we write in the final answer in prime factorization in index form, which would be 2 to the power of 2 times 5. This is known as the prime factors of 20. We can also look at 20 as 2 times 10. Now 2 is already a prime number, but 10 is not. So if we break down 10 to 2 times 5, we get the same answer. And you'll always get the same answer. No other number has a prime factorization of 2 to the power of 2 squared times 5, other than 20. You can use tree diagrams or tables to help you with prime factors. For instance, 90 can be thought of as 3 times 30. 3 is a prime number, so that branch is finished. 30 can be thought of as 2 times 15, and 2 is a prime number, so that branch is finished. And 15 is 3 times 5, which are both prime numbers. Now we've got all the final prime factors. We can write in index form 90 equals 2 times 3 squared times 5. So normally we write the prime numbers in increasing order. Prime factorization has some really good applications. The first we'll look at is finding the lowest common multiple of fairly large numbers. You probably wouldn't use this method for small numbers. Let's find the lowest common multiple of 180 and 144. First of all, we need to find the prime factors of 180. Let's go 2 times 90, 2 times 45, 3 times 15, and 3 times 5. So 180, sorry, I've cut off here. 180 equals 2 squared times 3 squared times 5. Now let's have a look at 144. 144 is 12 times 12, we all know that one, which is 3 times 4. I'm just circling the prime numbers just so I know that branch is finished, and 4 is 2 times 2. So 144 can be thought of as 2 to the power of 4 times 3 squared, because we've got 2 3's. Now, to find the lowest common multiple, we want to, and I'll write this nice and big, take the greatest power of each prime. So in this case, if we have a look at our prime factors for 180 and 144, for base 2, it's 2 to the power of 4. For base 3, it's 3 to the power of 2, doesn't matter which one we take. And for 5, it's just to the power of 1. So our lowest common multiple, I'll write this here, I'll squeeze right up. So our lowest common multiple of 180 and 144 is 2 to the power of 4 times 3 to the power of 2 times 5 to the power of 1. And if we're going to actually calculate this out, 2 to the power of 4 is 16 times 9 times 5, we get 720. Now, this is probably quicker than listing all the multiples of each number until you find the lowest common multiple, but for smaller numbers, the traditional method's probably faster. Now let's have a look at how to use prime factorization to find the highest common factor. Here, we take the smallest power of each common prime factor. So using the same numbers, 180 and 144, I'll just rewrite the prime factors here. So 180 was 2 to the power of 2 times 3 to the power of 2 times 5, and 144 was 2 to the power of 4 times 3 to the power of 2. And we're taking the smallest power of each common prime factor. So they have 2 and 3 base as common, and we're going to take the smallest this time, which will be 2 to the power of 2, and either of the 3 to the power of 2's, doesn't matter which one. So we can therefore write that the highest common factor, abbreviated HCF, of 180 and 144 is 2 squared times 3 squared, which is 4 times 9, which is 36. In other words, if you have a look at what we used before, when we found the lowest common multiple, we used 2 to the power of 4 times 3 to the power of 2 times 5. It's what's left over finds the highest common factor. Neat little trick. Another application of prime factorization is finding square roots and cube roots. So notice when we were looking at 144, we had 2 to the power of 4 times 3 to the power of 2. Since both of these indices are even, we could actually divide them in two. I'll just do this over here. So we could write it as 2 squared times 3 squared, which would give us 2 to the power of 4 times 3 to the power of 2, which would be 12 squared. So if we were asked to find the square root of 144 and we divided the powers into 2 even groups, we could easily find the square root. Let's have a look at using this method to find the square root of 324. Now, 324, I worked out earlier, prime factors are 2 to the power of 2 times 3 to the power of 4. Both of these indices are even, so they can be written in two groups, that is 2 times 3 squared times 2 times 3 squared, or in other words, 2 times 3 squared all squared. Now 2 times 3 squared is 2 times 9 squared, which is 18 squared. Knowing that 324 is 18 squared, we can therefore say, therefore, the square root of 324 equals 18. Use a similar method to find cube roots. Earlier I worked out 1,728 prime factors are 2 to the power of 6 times 3 to the power of 3. Now here the indices aren't even, so we couldn't find the square root of 1,728. But we can group these into 3, and we're asked to find the cube root. That's a little 3 there. So we could write it as 2 squared times 3 times 2 squared times 3 times 2 squared times 3. I've run out of room here, so I'm just going to write it as 2 squared times 3 cubed. That is 4 times 3 cubed, which is 12 cubed. Knowing that 1,728 is 12 cubed, we can then write the cube root of 1,728 is 12. Now there's other applications of prime factorization. One that you might have heard of is cryptology, which is protecting information, communicating it through the use of codes. So computers like to work with prime factors.